Marten Terpstra. I'm with Plexxi Product Management. Was here 2 NFDs ago, talked a lot about our switches, our optical capabilities, and those sort of things. So for this session, I want to talk a little bit more about our controller, and not so much the provisioning and the configuration and the debugging part of our controller, but more around the process of, how do we get to place traffic on the network, right? I mean, we at Plexxi are a firm believer that, regular protocols, routing protocols that we've known and loved for so long are doing an adequate job of moving traffic onto a network, but we think we can do better, right? If you started looking at the application, what is it that an application or a device or an appliance, if you started looking what does it need, and you can try and articulate that into a certain network behavior, we should be able to find that behavior or create that behavior on a network, assuming that we have a network that has that sort of diversity available to it. So in this session, talk a little bit about how do we go about taking information from various sources, crunching on it, and then coming out with how do we actually get traffic installed onto switches? How do switches actually forward that traffic? And then the second part of that is around customers, right? We have paying customers, which is always good as a startup. And these customers fall into a couple of categories. So I'm going to walk through some of these categories and articulate what they're doing with it, what their attraction to Plexxi is, and sort of what is it about the solution that has their emphasis that they fell in love with in a way that made them buy the solution. So first, this is our overall architecture. You may have seen a flavor of this slide. It sort of gets expanded every time we present it. And I've talked about the Plexxi switches, right? We've talked about the Plexxi switch in previous NSDs. In another session, I've talked about Plexxi Switch 2. Derek and Niels have talked about, and we'll talk about some more about the top layer in here, which is our integration. The part that we haven't really talked about much is how does the controller actually control the switches, right? We've mentioned it, we've articulated it in our blogs and some other places, but in this forum, we've never really explained how that worked. So I'm hoping that with a couple of pictures and some description, I can give you an idea of what kind of information goes into the controller, how does it make decisions about what needs to go where, and how does that ultimately lead to forwarding behaviors of switches, because that's ultimately their goal for packets. So in an extremely simplistic form, and in a way it is simplistic, except that the actual execution underneath that requires quite a bit of brains, which is why Mike keeps calling us a math company, is we have this concept of affinities, right? And if you've heard from us before, hopefully, we define network behavior in affinities, right? We believe applications should articulate what they need, and that articulation of a specific network behavior we call an affinity. An affinity is a relationship between a sender and a receiver, or multiple senders and multiple receivers that have a specific need. That need may be a lot of bandwidth, that need may be low latency, that need may be separation from all other traffic. In the future, that need may be that traffic needs to be intercepted or redirected. There's types of behavior. A description of the behavior of the communication between two entities is what we call affinities. You can articulate those, right? I mean, we have a GUI that allows you to articulate those. We don't necessarily believe that a lot of people will do that, right? These will be formed from integrations, right? We will receive those from higher level orchestration systems. Things like VMware may tell us that a certain VM has a relationship with a certain shared storage device. Those sort of things, we expect that all those affinities are being told to us through our APIs, right, that we get that information from higher level provisioning and orchestration systems. But ultimately, these end up being a set of strains, if you wish, a set of relationships with desired behavior. Data point number 1. The second data point, and I've talked about this in a previous session, is the switches amongst themselves create this mesh network. They connect to each other. They create this mesh of 10 gigi connections between them. That entire mesh, the switches will discover each other, will figure out who's connected to whom and where through our optical fabric. That entire connectivity, basically a 1 layer 2 connectivity. Can I reach you how can I reach you, who's connected to whom, is data point number 2. That information is fed from the switches to the controller. So the controller is actually learning from the switches, how are they connected to each other? Who is connected to whom? How many links do I have? From where to where do they go? It's my basic, topography is the ultimate word, but it's my basic layer 1 and layer 2 connectivity. What's my network look like? And then the last thing we do is we look at utilization statistics. The switches will actually tell us how much bandwidth is being used, how much is used on each one of their fabric links. So the switches will give an indication back to the controller, like, this is how much traffic I have flowing on my links. All of these 3 things combined then go into what we call fitting. And again, this is pure math. I know Mike has talked about that in the past. We always call them a bunch of PhDs, right? We have a bunch of PhDs that do nothing but go through algorithms to go and figure out, how do I take all of this, a physical topology, a set of desires or constraints, and an idea of what is currently floating, and how do I then make the best choices of how these guys need to be mapped onto this network while taking into consideration what I'm currently using. And oh, by the way, then there's the rest of the traffic. Because we are not expecting all the traffic to be articulated as affinities. There's lots of traffic that simply needs to flow, that has no specific need, it has no specific requirement, it just needs to get from A to B. Right? We're expecting the affinitized traffic to be a portion. 10, 15, 20% of the traffic is affinitized, the rest is just traffic that just flows. Layer 2, layer 3, doesn't matter, just flows. All of that combined is what the fitting engine, right, that's the piece of our controller that actually does that math, is what the fitting engine takes into consideration and actually walks through. And this is pure graph theory, right? This is a graph, and these are constraints that are being put on top of the graph. Outcomes a set of layer 1, layer 2, and layer 3 topologies. And we very specifically call them topologies. For some of these things, they are very explicit paths. Right? You may have articulated an affinity that says, I have a VM here and I have storage there, and I want these guys to have lots of bandwidth. We will create a very explicit path for that relationship, almost like, dare I say it, OpenFlow. Right? It is almost every switch along the way is told, when you have traffic coming from this VM going to that storage device, this is the port you're going out to. Comes into the next switch, it's being told very explicitly, when it comes from this VM, goes to the storage device, this is the port you're going out to. So that path is very explicitly created from end to end. Most of the traffic is not explicitly routed. Right? We do not have explicit entries for every single flow that we have. Right? We don't fill up the TCAM entries in Trident 2 with every single flow that can possibly go through a network. The rest of this is described in what we call topologies. And topologies are descriptions of how would I get to a certain destination. And by having a topology rather than a very explicit path, the switch now has autonomy to decide how to use that topology. Right? The topology is almost like I'm going to tell you the way to get there. I'm going to give you 6 different ways to get there, each one of them with a different weight. Right? I want you to take 10% of all traffic and I want you to send it that way. I want you to take 20% of the traffic and send it that way, all based on these calculations, because certain links may be busier than others, others may be empty. So those topologies are more a description of how do I get there, rather than I'm going to tell you exactly hop by hop by hop how to get there. These topologies, today they're mostly layer 2. Like I explained, because we have this optical cross-connect, we actually have the ability, the controller actually has the ability to change the layer 1 topology. If it believes that it needs to create more physical bandwidth between 2 switches, it actually has the opportunity to redirect bandwidth at layer 1 by changing the optical cross-connect, right, to move bandwidth to where it believes it needs to be done. Rarely done today, but the capability exists. Layer 3 topologies, like I said, today it's actually fairly straightforward. Everybody routes for every single VLAN, but the moment we grow this and start creating abstractions, we will also start to create these same forwarding decisions, these same choices for layer 3, not just for switching packets. We also start to think about how do I route packets without relying on routing protocols, actually let our calculations go and figure out how do I get routed traffic from A to B. those topologies are given to the switches. All the switches receive that two-phase commits, right? They receive that information. It's a description of topologies sent to the switches, two-phase commit. They all got to come back and approve that. And once that's done, all of the switches will start to act according to those topologies. So they all start to behave the exact same way. Very similar to how an OSPF network, right, once everything has converged, they all start making the same choices. Here they're not calculating the choices, they're being given the choices, but once they're given, they all start behaving the exact same way, right? And the nice thing about having a controller calculate this for us is we can actually create, and we've called them non-equal cost multipaths, right? We can actually send traffic, in one direction it may take 3 hops, in another direction it may take 2 hops. And it's perfectly fine because the guys along the way know exactly what they're supposed to do with it because all of them are working on the same set of forwarding behaviors.
So you said that the layer 1 changes are rarely made today. Do you have an opinion as to why?
So today you can change them manually, right? So you can go in today. That's what I explained with the DCI. I can go in and manually change the topology of layer 1 by manipulating the optical cross connect. Today, with the customers that we have so far, we haven't found the use case yet for these customers. And granted, right, it's a relatively small set at this moment in time that we can actually go and drive the how we do it on where will we base the decisions on. Right? Because so far, everything we found so far in all the calculations, all the math that we've done for them, is the capacity is plenty for them. So we haven't had a need to go and move capacity around. We will get to that point, right, where there will be a customer that has needs that are beyond our current default topology, right? We create a default topology of how our switch is connected. All of today's customers fit well within that default topology. That's one of the reasons why we haven't gotten to the capability exists, but it's one of these, how do we tune this? What does this customer want to do with it? How do they want that to behave?
Then would it be a safe assumption to say that the layer 2 and layer 3 topology for the same traffic flows would just mimic or overlay the layer 1 topology?
Correct. Right? They all work in tandem, right? If we decide that we need to change the layer 1 topology, then we will create a layer 2 topology that fits on top of that renewed layer 1 topology, and the same for layer 3 topology. Right? So they're all built on top of each other.
So in the past when we've talked to you guys, it's come up the fact that because you have all this data that you're gathering and because you can talk to external systems, whether it be vSphere or other structures, the best solution might not always be to swing path around and pipes around, but because we understand affinities between servers in a highly virtualized environment, it might make more sense just to go ahead and queue vCenter to move that workload so that's in the same cluster and it actually has a higher bandwidth path there. Is that what you're talking about? Is that what your customers are experiencing now?
So they haven't even gotten to that point yet, right? So the current customers that we have, and you're absolutely right, this works in 2 ways, right? There is the network can adapt to what you want, or we can go and tell the compute or storage controller, you really don't want to do that. Right? We have knowledge about what is hot in a network, right? Because in this picture that I had here, right, utilization statistics, we keep track of this. The controller gets fed these utilization statistics. It knows exactly how much traffic is coming in out of each fabric port, out of each server port. We can actually provide that feedback, right? We can actually feed it back to vCenter or whoever and say, there's currently no way of actually inputting that information into vCenter that says, I prefer you move it not here or somewhere else. Certainly that capability. Haven't gotten there yet with the current customers.
Okay.
I mean, the amount of bandwidth that we create within the network is, for the current set of customers, well beyond what they need today. Which is why some of these things, while we thought about it, we think we have solutions for them, we haven't put them in practice yet because there hasn't been a driving force there just yet. 20 minutes for the demo session. Okay. Now, and when you take these topologies, and I sort of mentioned this, right? When you take these topologies and then feed them back into the switches, they essentially come in 3 types. The first one is the easiest to understand. It's a fully specified path, right? These are what you have a very explicit affinity created between 2 endpoints, and you want to say, I want traffic to go from here to there. Every step along the way is forwarded. Right? It's a fully specified path. Every switch is aware of that traffic flow. Truly a flow that's almost programmed to all the switches. The second one, and I tried to make that term as long as I possibly could. We call it partially specified, or a non-equal weighted egress-based multipath tree. I did that on purpose. They're all true, but it's a little bit overweight. But the idea is that this is a description of how do I get to a certain destination. And there's multiple paths to get there. They may not all be the same weight, right? So they may not all be 1 hop or 2 hop or 3 hops. They may be 4 or 5 hops away. They're weighted because the path, the calculations have said I have certain links that are really busy, other ones that are not really busy. I want you to use 10% here, 20% over there. And the last one is they're based on egress. They're based on where am I going. Right? So it's a tree that's created based on where am I going. This is where most of the traffic will follow these. Right? All of the traffic that you haven't explicitly specified, you haven't explicitly created an affinity for, will flow this way. Last thing, backups. We talked about this in previous sessions. We also calculate backup paths, so we don't have to go when something breaks. We don't have to go back and recalculate. The switches have already been told hundreds of backup paths for all of these. So when a link fails, when a switch fails, they know exactly what to do. Customers. So here's the customers, and they're not mentioned by name. There's some that I can, probably offline. Others probably not yet. So the first one is this is a small to medium public cloud provider. They're KVM, virtualized based, international. They have, essentially, they have residents in a lot of data centers around the world. They buy places in data centers from Equinix and all the other places. For there, it was actually relatively simple. I'll let you read all this. You have the slides later. For them, it was. They currently had network that had sort of separated their storage from their customers. They had lots of provisioning issues. They constantly had to go in and change something, right? Change a VLAN, add a VLAN, add a subnet, change QoS, right? They constantly had to go in and touch the switches every time a new customer came along. And they needed more bandwidth. They were migrating from 1 gig servers to 10 gig servers. So they were looking for that next sort of phase up. For them, the biggest driver for all this was a direct integration with their portal. So they have a portal like you see from many other places. You can go in, how much virtual CPU do you want, how much virtual memory do you want, how much disk space do you want, please put your credit card number in, and voila, in 10 seconds, 30 seconds later, here's all the data you need. And what we did for them is, again, this was very much integration driven. We helped them write an integration from their portal into our provisioning system. So every time they had a new customer that came in, registered online, put in their credit card number, while their KVM sort of provisioning system went off and started firing off VMs, we took that information, made sure that VLANs were provisioned on the right hosts, that if there were relationships between this VM and storage, that they were provisioned, right, all the right provision happened on the network side. So for them, really, out of all the things that we do, right, the biggest benefit for them, these are fairly small, right? They had 2 or 3 switches in each one of their data centers, so they didn't make a lot of use on the, the grand fabric kind of thing. 2 or 3 switches. Their key point, integration. The second, a similar sized public cloud and hosting provider in Southern California, 1 gig server based, right? They had something in the order of 11, 12,000 1 gig servers with a very slow roll to 10 gig. So not really a match for us as a direct server connectivity, but they were looking to replace their core. Right? How do they connect? They had multiple data centers in a campus kind of environment, multiple buildings in a campus kind of environment. Had it connected with regular layer 3 switches, and again, this goes back to your case, Greg, at a slightly smaller scale, is they had when someone needed VMs, when they needed to be hosted, they always needed to find a location nearby where their other VMs were hosted, their other bare metal servers were hosted. They wanted the flexibility to simply provision this across any of their data centers within that campus area and simply stretch the VLANs from one place to the other without having to worry about it. Again, they were stretching it not to turn them into large scale, because these are all VLANs that had 10, 20, 30 devices on it, but simply the flexibility of allowing that to be stretched and routed on ingress, what was the biggest driver for them. They also had a separate storage network. They had a couple of really large iSCSI arrays that they used to serve everything else. They created a separate network for them. With us, they've actually converted onto a single one, and we have actually separated the storage traffic. So we've isolated the storage traffic from all the other traffic, giving them essentially a dedicated 10 gig storage network on top of the same infrastructure. This is a case that's sort of halfway into public cloud versus layer 2 transport. This is a very large public cloud provider, but very focused on storage. So they provide storage solutions. They either provide it in-house, you can essentially sort of buy storage with them, or they give you space, but very specifically dedicated to storage and archiving kind of things. You'll see these. I can't mention these guys' name just yet. They'll probably come out with a press release. They're on the East Coast, probably one of the biggest public storage places that exist. They had two requirements. One was distance, because of the way their facility was laid out. Is that they had kilometers between places within their facility that they needed to reach. So the fact that we had built-in 10-kilometer optics was simply a plus for them. It was very convenient. They could run that. They had a full single-mode infrastructure, so that was a quick match. Second one was they needed to stretch VLANs. They provide layer 2 VLAN access to storage solutions for customers. Customer would bring either a carrier Ethernet kind of device or whatever in there, and they would provide layer 2 transport out to the storage that was dedicated to the customer. So layer 2 transport end to end. Today VLAN separated simply because the size of it, and that was fine. They do want VLAN translation. They wanted us to change the VLAN on ingress or egress. At some point these guys will want to go virtualize one level up because they'll grow out of VLAN space. Last thing they do, and this again comes back to those flex ports, they have some customers that are actually willing to buy capacity from one side of the facility to the other side of the facility. Right? They may have some hosting. Big customers have some hosting devices on one side and storage shared or otherwise on the other side, and they're actually willing to buy a private 1 to 10 gig connection from one side of the facility to the other side of the facility. We actually solve that for them with our flex ports. Right? We give that customer a flex port SFP plus, 1 gig or 10 gig. We map it onto our fabric, right? Take one of the optical links, spits out another way, spits out on the other side, and it's a completely transparent layer 1 connection. There's no packet processing in the middle, a private interconnect between these two places for that customer without having to worry about fiber. I'm getting the stop now signal. I got one more slide. Last slide, very similar to the DCI case that I talked about. Customers layer 2 transport, so they have Metro Ethernet devices that sit on the edge. They want a very dynamic fabric that has most of the optics interconnected. I talked about this case very similar to this, right? Flex ports moving of capacity. The one thing I haven't talked about, and I'll let you read this later. So they have DWDM transport. They are looking for 300 gig between data centers. That's sort of the capacity these guys are looking for. They're essentially a carrier looking for layer 2 transport, and within they're starting this in Florida specifically, within their locations, right? They really are about 4 switches each in these locations. They're looking for 300 gig between these, and these sort of get scattered onwards. 300 gig of bandwidth, not just pure bandwidth, but bandwidth that they can manage from where it goes, right? So it's not just between these 2 switches. It goes an optical connection from here to here, from here to here. They can completely control where that bandwidth goes. So for them, that FlexPort connectivity and the ability to dynamically place that where they want through the optical cross-connect was the biggest driver for them.